All right, moving on to the last page here, right, and we'll be wrapping up Chem 151 here with this these last two problems. So first off, we've got another gas law problem. We've got a gas phase organofluorine compound. We're given the density, temperature, pressure. We want to calculate the molar mass. So I think similar to the problem we looked at earlier, there's a couple different ways to go about solving the problem here, although all would involve recognizing that molar mass would be grams per mole. So I would kind of just use units to work through this problem. So I would start with the fact that I was given the density. That would provide grams on top of my units. Right, and I would put liters at the bottom here and then use liters to figure out what to add next to the calculation. So if I want to cancel out liters, the next thing I'm going to want is gas constant. So 0.0821, that would put liters and atmospheres on top of the units, kelvins and moles on the bottom. Liters goes away. So now I've got moles as well. Grams I want, moles I want. And what I need to do now is get rid of these other two units, the pressure and the temperature. Now, temperature, I've got to convert to Kelvin. So if I add 273 to my 17 degrees Celsius, that would be 290 Kelvin. And in this case, I can multiply by that to get rid of the kelvins there. And then I'm going to have to divide by the pressure in atmospheres. Now, the pressure given is actually in millimeters of mercury. So let's get out of atmospheres first. So I'll change the pressure in my calculation to millimeters of mercury. Then I can divide by the 189 millimeters of mercury here to cancel that out. Right, and then I'm left with grams per mole, which is the molar mass. That's what I want for the problem. So, calculator went to sleep. 0.355 times 0.0821 times 290, times 760 divided by 189. That comes out to be, looks like three significant figures here. So rounding would be 34.0 grams per mole. Right. Now this particular problem, right, we could do this with PV equals nRT as well. PV equals nRT. Now having the density, we've got the mass in there. So again, sub mass divided by molar mass in for N. That would be mass times RT over molar mass. If we want to solve for the molar mass, we can just put the molar mass by itself on one side, everything else by itself on the other side. So if I multiply both sides by molar mass, I would get molar mass, and then divide both sides by P and V, mass RT over P V. And that would mean I take the mass, multiply by the gas constant and the temperature, which is right here, mass times gas constant times temperature, divide by the pressure and the volume, divided by the pressure there, and I actually divided by the volume back here by putting in the density. 1 liter is the volume that goes along with density. So you could solve the problem that way and then plug in here as well. There's actually a third option here as well, in that since you have the pressure and the temperature, and you kind of do have the volume, you could use this pressure, this temperature, and 1 liter to figure out how many moles of gas you have. And once you have that, you could take the mass and divide by how many moles, and that would also get you to your answer. Now, another way we could adapt this problem, now that we know it's 34 grams per mole, and we know it's an organofluorine compound, that means carbon and fluorine. Well, if you have 1 carbon, that would be 12. 1 fluorine would be 19. You're pretty close to there already. That would be 31 grams per mole. So the formula here looks like it would involve 3 hydrogens in addition to the fluorine. So this molecule would maybe look like that. That would match that molar mass. 1, 2, 3, 15, plus 19 would be 34. So this would be 1 fluorine attached to a carbon with 3 hydrogens. right? Might be a nice part B, right, or a bonus question at the end of that problem. Okay, the last problem here. Calculate the atomic mass of potassium if the abundance atomic masses of the isotopes, there probably should be an and in there, if the abundance and atomic masses of the isotopes making up its naturally occurring samples are as given below. So two isotopes, 39 and 41, were given abundances and masses, and this really just means we need to plug into our weighted average formula. So atomic mass will be equal to the mass of each isotope, I'm just going to number them, times its abundance, the abundance of number one, and then there'll be a separate term for each additional isotope that makes up the sample. And that could be any number of isotopes. It's only two in this case, so we can stop, but there would kind of be ... there for potentially a third isotope or even a fourth, fifth, sixth, whatever. So plug in the masses here, 38.964. And the abundance, right, relative abundance, that is kind of describing the fact that there's a percentage here. We don't want a percentage in this calculation because that's artificially multiplied by 100. So if we pull out the 100, the abundance is 0.9312, right? And then do the same for the other isotope, 40.962 atomic mass units there. And if we divide that one by 100, that would be 0.0688, right? And that 0 is actually a big issue here. If you make this just 0.6, that's more like 68%, not 6.8%. So make sure that those two abundances add up to 1 there. Easy to forget that 0. Okay, so if we multiply these together, 38.964 times 0.9312. Okay, this one comes out to be 36.283 atomic mass units, and then the second one, 40.962 times 0.688. I'm going to add 2.818. Now, this is going to be our limit here. This abundance is only 3 significant figures. So at the end, we're going to have to think about this is limited to 3 significant figures here. Now, 3 significant figures here would be the second place after the decimal, right? We have 4 here that would also be the second place after the decimal. So our answer should be limited to the second place after the decimal, which would be 39.10 atomic mass units. And that actually matches pretty nicely with what we see on the periodic table for potassium, 39.10. And it certainly makes sense relative to the two masses we're using in the problem, right? If we're doing a weighted average and we're using 38.9 and 40.9, our answer better be in between those two. Otherwise, something has gone wrong in our problem, right? And that's how you maybe would recognize if you forgot to pull out the hundreds here, or if this became 0.688, which is the common mistake I mentioned before, instead of 0.0688, this might end up 28, and then your number here doesn't make sense relative to the data you started with anymore. Okay, that's the end of the practice problem set. Hopefully that goes a reasonable way to getting you ready for the final exam. So keep up your studying, and I will see you at the final exam.